Hello folks, in this lecture we shall discuss about nuclear physics. This is the first lecture on nuclear physics. There will be one more lecture that will be uploaded very soon. So let us start. The basic outline of this lecture is like this. We shall discuss about nuclear composition, nuclear properties, the factors that decide the stability of nuclei, something called binding energy we shall talk about in detail, liquid drop model and shell model, which provide the theoretical explanation for binding energy. So first of all, let us discuss about nuclear composition. Nucleus contains two type of particles, proton and neutrons. The simplest atom, the simplest nucleus is of hydrogen, which contains one single proton. Deuterium is the next. It contains one proton and one neutron, and tritium contains two neutrons and one proton. Atomic number of all these three are same, but mass number is different because of different number of nucleons. The most abundant isotope is the first one. It is 99.9% in fraction, and the least abundant is tritium. Water, if made up of deuterium instead of this hydrogen, is called heavy water. The way of representation of a particular isotope is this. We represent it like this. X indicates its chemical symbol, A is for mass number, and Z for atomic number. Now let us talk about nuclear properties. First of all, let us know what is the typical size of a nucleus. Nucleus has size of the order of femtometers. An experimental method to know the size of a nucleus can be alpha particle experiment, the famous Rutherford's alpha particle experiment. Alpha particles can be used to determine the size of a nucleus by using Coulomb's law. Coulomb's law can be used to determine the size of the nucleus provided the distance between two neighboring nuclei is greater than 10 raised power 14 meters. The Coulomb law remains valid only under this condition. If the distance between two nuclei is less than that, Coulomb law does not hold good in this type of condition because the nucleus cannot be considered as a point charge. So in that case, this method of alpha particle scattering fails. So we need a better method for that. A better method can be the usage of electrons and neutrons. Electrons interact with the nucleus by means of electric forces, and neutron interacts with the nucleus by means of nuclear forces. Electron scattering provides the information about the charge distribution on the nucleus, while neutron scattering provides the information about the mass distribution of mass on the nucleus. So electron scattering provides charge distribution, information about charge distribution, because electrons are charged particles. Neutrons are not charged particles. They provide information about the mass distribution, the way neutrons and protons are arranged. This information is provided by neutrons because neutrons interact with protons and neutrons by means of nuclear forces. An important condition for accurate measurement is that the de Broglie wavelength for both these particles should be smaller than the typical size of the nucleus for accurate measurement. Once we know the size of the nucleus or radius, we can easily determine its volume and its density. We know that if R is the size of the nucleus, considering it to be a spherical, considering it to be spherical in shape, the volume of the nucleus should be this. And we know, we understand, it is easy to understand that nuclear volume depends upon the number of nucleons it contains. So nuclear volume is proportional to the nuclear mass number. That means radius, typical radius of the volume of the nucleus is proportional to the mass number, or in other words, r cube is proportional to mass number. So in this way, r is proportional to cube root of the mass number with r naught, like, and represented with r naught like this. Here r naught is the constant of proportionality, r is the radius of the nucleus determined, and a is the mass number of that nucleus. R naught, value of R naught is this much, 1.2 femtometer. Femtometer means 10 to the minus 15 meters. So R naught here is 1.2 femtometer. If you know the mass number of a nucleus, multiplying it by R naught, you can determine the approximate size of the nucleus, the approximate radius. Why it is approximate? Why not accurate? This is because nuclei don't have sharp boundaries, they have hazy boundaries. So we can do nothing in this. We can only get accurate approximate values, not accurate values. Excuse me. Now nuclear density can be determined by simply using this formula, mass upon volume, where mass is the atomic number multiplied by mass of the proton or mass of the neutron. M is determined like this, and if it is divided by the volume of the nucleus, it will give you the nuclear density. Typical nuclear density of a carbon atom is this much. It is equivalent to 4 billion tons per cubic inch. That means 4 billion tons of weight if it is condensed into 1 cubic inch of volume. 4 cubic tons of mass is condensed into 1 cubic inch of volume. The density that we get in this enormously dense situation, this enormous density is the typical density of a carbon nucleus. So you can see that this density is very high density, extremely dense. Nucleus is an extremely dense entity. Now coming to the stability, we see that there are nuclei which are quite stable while others are not. For example, radioactive materials, their nuclei are unstable and disintegrate on their own into smaller stable nuclei. So why are some nuclei stable while others are not? This depends upon their constituent, the number of nucleons they have, and the number of nucleons of each type they have. It is generally seen that smaller nuclei are more stable, having mass number less than 20 are more stable, and they contain equal number of neutrons and protons. Nuclei which contain equal number of neutrons and protons show more stable nature than those in which this number is skewed. If there is an asymmetry in this number, suppose neutrons are very large, number of neutrons is greater compared to the number of protons, the stability of the nucleus shall be lesser compared to those nuclei which have equal number of n and z. This thing is evident from this graph. You can see x-axis indicates the atomic number and y-axis indicates the number of neutrons, which is mass number minus the atomic number. Now you see that this line corresponds to the z is equal to n situation, and these are the various elements plotted. You can see that as the atomic number increases, this graph deviates more and more from the z is equal to n line. This happens this happens because heavier nuclei have more number of protons than more number of neutrons than the number of protons, because it is necessary for them to have extra number of neutrons to acquire stability. So the tendency of n equal to z, which gives rise to the stability, comes from the Pauli's exclusion principle. You know that electrons are spin half particles. Just like electrons, neutrons and protons are also spin half particles. They arrange themselves in nuclear energy levels just like electrons arrange themselves in atomic energy levels. The energy levels of atom, they are filled by electrons according to the Pauli's exclusion principle. In the similar manner, the energy levels of the nucleus are filled by these nucleons, protons and which are protons and neutrons, according to the Pauli's exclusion principle. That means one energy level can be occupied by only two neutrons and two protons. Two neutrons are of opposite spin and two protons of opposite spin. This arrangement of various nucleons in various energy levels in the nucleus will be clearer from this picture, and its significance is illustrated in this. To explain about the significance of arrangement of nucleons in the energy levels uh, in providing the stability to the nucleus has been illustrated using these two type of nuclei, the boron 12 and carbon 12. You see that they both have same mass number. That means the number of nucleons they have is same, but the number of protons is different, hence the number of neutrons is different, but the total number of nucleons is same in both of them. Now you see, if you look at three different isotopes of boron, the boron 10, boron 11 and boron 12. In boron 10, the arrangement of neutrons and protons is like this. You see, at each energy level, there are two neutrons of opposite spin and two protons of opposite spin. At the this highest filled energy level, you see highest occupied energy level, you see that there is only one neutron and one proton. In boron 11, there are two neutrons and one proton. These two neutrons are obviously of opposite spin. And in case of boron 12, you see something interesting happens, because in boron 12 there is an extra neutron and it has spin same as this one. This neutron has spin same as this one, so it cannot be occupied in this energy level. It cannot stay in this energy level. This energy level can be occupied only two neutrons of opposite spin. So this space is vacant for an extra proton but not for an extra neutron. So this neutron has no choice left but to accommodate itself on a higher energy level. However, it stays alone in that energy level, but still this is all it can do. It cannot sit at this energy level, because that will be the violation of Pauli's exclusion principle. So it stays over here. Now if you compare boron 12 with the arrangement of carbon 12, you see carbon 12 has all three energy levels filled. It has same number of nucleons, but has the same number of total number of nucleons in carbon 12 is same as that in boron, but the number of protons is equal to number of protons. It has 6 neutrons and 6 protons, which was not the case in case of boron. So these nucleons are arranged like this. So there is no need of occupying the high energy level. All of them are easily accommodated in these three energy level. So obviously, uh, from this arrangement it can be understood that since higher energy levels have been occupied in case of boron compared to uh, carbon 12, boron 12 shall be uh, of lesser stability compared to carbon 12, because because of its high energy levels. The energy level, the topmost energy level is higher compared to carbon. This is why carbon 12 is stable while boron 12 is not stable. If in any nuclear reaction boron 12 is generated, is produced, it immediately disintegrates into carbon 12. It immediately changes itself into carbon 12 by emitting out a beta particle. By emitting out a beta particle, it converts this extra proton, this extra neutron into proton, and the proton comes and sits over here. So from an unstable arrangement, in this way it acquires a stable arrangement. Now we know that the two protons are of same charge, hence they repel each other, while neutron is does not have any charge, is chargeless. So the force between two protons shall always be repulsive, because of the same charges, and force between proton and neutron, the electric force between them, shall be attractive. So this is why, as the uh, atomic number or number of protons increases in case of heavy nuclei, uh, extra number of neutrons are required to hold the protons together and form a nucleus. This is why you see the protons are positively charged and repel one another. So in case of, as I told you, that for mass number greater than 20 or atomic number greater than 10, the repulsion between protons becomes so great that extra neutrons are required to achieve stability. These neutrons and the attraction force between the protons and neutrons try to overcome the repulsive forces between proton. The proton repulsion is overcome by neutron proton attraction. This is why it has an extra number of neutrons and number of protons need not to cannot be equal in heavy nuclei, because that will not be sufficient for the stability of the nucleus. So extra neutrons are required, because proton neutron attraction needs to overcome the proton proton repulsion. This is why it has an extra number of neutrons. N is equal to Z does not uh, is not true in case of heavy nuclei. Extra number of neutrons are required, and most important thing, that it is never ever seen that N is less than Z. Number of neutrons can never be less than number of protons. Number of neutrons can be equal to number of protons in light nuclei, and number of neutrons is needed to be greater than the number of protons in heavier nuclei for better stability. But it is never ever seen that number of neutrons is less than number of protons. So this is very important. Now one more pattern in stability has been seen, that there are there can be even number of protons and even number of neutrons in a nucleus. It has been observed that the percentage of even type of nuclei, which has even number of protons as well as even number of neutrons, is maximum. 60% of the nuclei are even type, and around 40%, a little less than 40%, are of even odd or odd even type. That means either the protons are of even number and neutrons are of odd number, or the protons are of odd number and neutrons are of even number. The fraction of these type of nuclei is around 40%, little less than that. And odd type of nuclei are very rare. They constitute less than 0.1% of the total, and only these five nuclei are of odd type. These five nuclei have odd number of neutrons as well as odd number of protons. Now we come to a very important aspect called binding energy. Binding energy is something which is very important uh, from the stability point of view. You know, the idea of binding energy comes from the fact that it has always been seen that the mass of the nucleus is always slightly less than the total mass of the number of nucleons of which it is made. This has been observed always. For example, in this case, you see a hydrogen atom and a neutron. They have these values of masses. The total becomes this. When they come together to form a deuterium atom, the mass of a deuterium atom is this. You can see easily that these two numbers are not equal. The mass of deuterium is slightly smaller than the total mass of neutron and a hydrogen atom. So why is this mass less than the total mass of the constituents? Where has this defect mass gone? Answer is that defect mass appears as binding energy. Binding energy is, as the name suggests, is the energy which holds the nucleons together strongly to form a nucleus. Because of the binding energy, the nucleus exists. If you want to break a nucleus apart into its constituents, binding energy is the amount of energy that is required to be supplied. For example, in this case, typically, if you need to determine the binding energy, this much is the mass defect in atomic mass unit. Multiply by this, we get 2.224 million electron volt. That means binding energy that has appeared in this much of the atomic mass has converted into energy and has appeared as a binding energy in this nucleus, which is equal to 2.224 million electron volt. This happens in every nucleus. The binding energy, the mass, a slightly small amount of the mass, total mass, amount from the total mass of the nucleons appear as the binding energy in the nucleus. Experimental evidence of this value comes from the fact that to break deuterium nucleus apart into its constituents, 2.24 million electron volt energy is required to be supplied. Any energy less than 2.24 million electron volts will not be able to break the nucleus apart. It will remain as it is, and any extra amount of energy than this will be used as the kinetic energy of the two nucleons as they fly apart after breaking down of the nucleus. So this is a very interesting thing to understand about the nucleus structure. Now, as I already said, that energy equivalent to the missing mass or mass defect of the nucleus is called the binding energy, and it is given by the total mass of the nucleons minus the mass of the nucleus formed by them multiplied by this value. Now you know that if you talk about the typical values of binding energy, you will be astonished by the fact that these values are quite high, very high. These values are very high. There are not any, there is no other counterpart of these values, and which shall be reflected in this example below. You see, we know that binding energy of deuterium is this much, and maximum binding energy has been observed to be equal to 1640 million electron volts for 209 bismuth. It is an isotope of bismuth for which binding energy is this much. So this is so it has been seen that binding energy can vary from 2.24 million electron volts to 1640 million electron volts. Let us take the smaller value for this for our comparative study, and let us represent it in terms of kilojoule of energy per kilogram of mass instead of million electron volts, because this seems to be more comprehensible type of unit from the practical point of view. Now, if you convert 2.24 million electron volts into kilojoule per kilogram of mass, you see that it comes out to be 800 billion kilojoule per kilogram. 800 billion. This is a whopping number. This number is astronomical. Now, if we compare it with the heat of vaporization of water, in the same units, we see that heat of vaporization of water is 2260 kilojoule per kilogram. 2260 kilojoule per kilogram, the heat of evaporation water seems to be minuscule compared to this whopping number. If you look at a greater number, uh, uh, we can take the example of heat produced by burning gasoline. By burning gasoline, this much energy is generated. Uh, 4.7 tons per 14 kilogram, 14 kilojoule of energy is generated by burning uh, 1 kilogram of gasoline. So you can see that comparing these numbers, you can see that 800 billion is astronomical compared to a minuscule 2260 kilojoule per kilogram and 4.7 tons per 4 kilojoule per kilogram. This is quite a big number, but it is still a dwarf compared to this value. Binding energy per nucleon. You know, binding energy is responsible for the stability of the nucleus, but binding energy is not the accurate measure of the stability, because same binding energy, if there are two nuclei of same binding energy and one of them is smaller and the other one is larger, same binding energy will be able to provide greater stability to a smaller nucleus than the bigger one. So instead of binding energy, a more accurate uh, measure of stability is binding energy per nucleon. This is why this term has been uh, invented, because binding energy per nucleon gives you an accurate idea of how stable a particular nucleus is. Now you see that in the previous example of deuterium, we saw that 2.24 million electron volt was the binding energy for deuterium atom. It contains two nucleons, a proton and a neutron. So binding energy per nucleon is 1.1 million electron volt. For bismuth, binding energy per nucleon is this much, 7.8 million electron volt per nucleon. If you go on determining this value, binding energy per nucleon, for various types of elements, you get this type of graph. And in this graph, you see that there is a maximum value. The maximum of this value corresponds to the atomic number of corresponds to the mass number of 56. The mass number of 56 is seen in case of iron. An isotope of iron has mass number of 56, and if you determine try to determine its binding energy per nucleon, it comes out to be 8.8. It is even greater than that for bismuth. So in all the elements, in all the types of isotopes existing. This the iron 56 isotope has the maximum binding energy, that is equal to 8.8 million electron volt per nucleon. That means iron 56 isotope is the most stable nucleus. So a general rule, a general inference that comes out of this discussion is that greater the binding energy per nucleon, greater is the stability, which is clearly indicated in this case that maximum stability of iron 56 nucleus is because of maximum binding energy per nucleon. Now you see the graph that we saw on the previous slide, this graph. If we get a particular graph or a pattern from experimental observations, it is always desired that there should be a theoretical model to explain that nature. So people worked a lot on this, and Gamov and Wiesacker came up with this liquid drop model to explain the pattern of binding energy, the the change of the variation of binding energy with respect to mass number. uh, in their model is called liquid drop model, because they compared the nucleus, they compared a nucleus with a drop of a liquid. Just like a drop of a liquid tries to remain spherical because of the surface tension, this is why in the similar manner nucleus also tries to remain as spherical as possible. So it can be compared, it has been compared in this model uh, to the drop of a liquid. We shall see it in a bit detail. Suppose a nucleus has a certain number of nucleons. A particular nucleon bond has some value of energy equal to U. This U is should be negative because nucleon bond is attractive in nature. So energy associated with the attractive forces is always negative. But for convenience and convention, we shall take U. We shall take, because we are considering binding energy as positive, so we shall consider it positive, because binding energy is defined as the experimentally it is defined as the energy that is required to be supplied to a nucleus for breaking it apart into its constituents. So this is why we shall in this entire discussion we shall consider the binding energy to be positive instead of negative, though it is associated with attractive forces, but this convention is used in nuclear physics. So now, as we have assumed that U is the binding energy, U is the energy associated with one nucleon bond, and in a nucleon bond, you see that this bond is shared by two nucleons. So U is being shared between two nucleons. So in this way, binding energy per nucleon is U by 2, obviously. Now suppose these various nucleons are arranged in a spherical manner as tightly as possible. The sphere is as tightly as possible, because as I already said, we are considering it to be a drop of a liquid, and drop of a liquid tries to confine itself in the least possible volume, and that can be done by acquiring the shape of a sphere. So sphere has the minimum volume. So on the similar lines, a nucleus also tries to pack itself in the minimum possible volume. So nucleus tries to remain as spherical as possible. So suppose if this is the case, each interior nucleon, a nucleon which is present inside, each interior nucleons in a closely packed spherical arrangement is in contact with two other neighboring spheres, two other neighboring nuclei. So if it is contact with two other neighboring nuclei. So in this way, each interior nucleon has 12 times of u by 2 is equal to 6 u of the binding energy. According to liquid drop model, we have considered over here the since we already know that binding energy per nucleon is u by 2, and each internal sphere is in contact with two other neighboring spheres. Spheres in this case are the nucleons. We are considering nucleons to be spheres, small spheres which are arranging themselves in a spherical manner. So each nucleon is in contact with 12 neighboring nucleons, and in this way the binding energy per nucleon in this type of arrangement for a nucleus in the interior is shall be this 6u. Now if each nucleon has binding energy of this 6u. 6u is the binding energy per nucleon, and there are 8 nucleons in the nucleus. In that case, the total volume energy shall be 6 AU, or it is simply written as this: EV is equal to A1A. This energy is the volume energy, which is because of the volume arrangement, the arrangement in the volume, because of arrangement in the volume of minimum volume. So this is called the volume energy. But you know that in coming to this formula, we have assumed that all the nucleons in this nucleus we are considering them to be interior nucleons, but which is not the practically possible. There are always nucleons present on the surface. So some nucleons are there on the surface too. Few of them are in the interior and some of them are on the surface. So on the surface, the nucleons which are present on the surface, they are not able to remain in contact with 12 neighbors. They don't have 12 neighbors, only the interior nucleons have 12 neighbors. Those on the surface have neighbors less than 12. So this is why this is not the accurate value of binding energy. Volume energy is one component, but it has to be reduced by certain other factors. Considering the surface effects, we come up with a different type of energy. Now let us see the surface area is given by this 4 pi r square. R is represented in terms of mass number like this. You see that if you see that all these factors are constants, and if I write it down with a single constant of proportionality, I can the energy that comes out over here because of the nucleons present at the surface is this: Es is equal to a minus a2 into a raised to power 2 by 3. This energy is negative in nature because it tends to reduce the binding energy, and it is by the virtue of the fact that nucleons which are present on the surface, they are not able to remain in contact with 12 nucleons. So their neighbors are less than 12. This is why we need to consider the surface effects also. From the surface effects, this expression comes out. This is called the surface energy, and it is negative because it has this tendency of reducing the binding energy. This is why it is negative. Now surface energy is significant in case of small nuclei, because in case of small nuclei, a greater fraction of nuclei are present on the surface, while in case of large nuclei, most of them are present inside and only a smaller fraction of them are present on the surface. So surface energy becomes significant in case of smaller nuclei and are lesser significant in case of larger nuclei. You see that in this picture formation of a drop has been shown, and it can be seen that the drop tries to acquire a spherical shape in case of any external disturbance. So same is the case with nucleus tries to become as spherical as possible. Now besides surface effects, there are Coulombic repulsion also. You know that two protons tend to repel each other. So the potential energy between two protons is, which are at r distance apart in the nucleus, there are two protons which are separated from the distance away, separate from each other by the distance r. The potential energy between them is given by this. And if the z is the atomic number of the nucleus of that element, so these many pairs of protons are present inside the nucleus, and because of these many pairs, these many we multiply by this shall be the total potential energy because of the proton proton repulsion, the Coulombic repulsion. In this case again, the Coulombic repulsion is trying to reduce the binding energy or trying to destabilize the nucleus. So this is why Coulombic energy is also creating a negative effect, hence it shall be considered negative. This is why negative sign has been put over here. So Coulombic energy comes out to be the number of pairs of protons multiplied by the potential energy of each proton proton pair, which comes out to be this, where 1 by r average is the average distance between two protons, and upon further simplification we see that it comes out to be this. Why this? Because 1 by r is proportional to 1 over the is 1 by r is proportional to the 1 by capital R. Capital R is the radius of the nucleus, and capital R is proportional to cube root of mass number. So it is always better to write things as we have been consistently doing, that we are writing all these formulae in terms of mass number. So this is same thing will be done over here, that we shall write this formula of Coulombic energy, the Coulomb energy which arises because of repulsion. We shall write it in terms of mass number and atomic number, and this A3 is the constant of proportionality for this energy. This is called Coulombic energy, and it is again negative because it has this tendency of reducing the binding energy and stability. Now beside these three, there are two more effects, and hence two more type of energies which are negative to the binding energy. First one here is the asymmetry energy, which arises because of asymmetry in the arrangement of nucleons. Suppose we have a nucleus having equal number of neutrons and protons, so they can be arranged in the energy levels like this. Now from this type of nucleon, uh, if uh, if we now consider a nucleus this type, from this type of nucleus, if we now consider a nucleus which has 8 extra neutrons, so these 8 extra neutrons can be produced, can be formed by transforming 4 protons into neutrons by giving out beta particles. Now see, uh, 4 protons of n is equal to z type of nucleus shall be shall be replaced by 4 neutrons in this type of arrangement, and you see that this one which has extra number of neutrons, it acquires greater number of energy levels. The one which has equal number of neutrons and protons, just like the case of boron and boron 12 and carbon 12, we see over here that though the number of nucleons is same, the mass number is same, but this has equal number of neutrons and protons. But this however the second case has greater number of uh, neutrons in it. So these extra number of neutrons shall be arranged in the higher energy levels. So it will give rise to a reduction in the binding energy. Why? Because because the work that is required to be done for for this type of to acquire this type of arrangement from this type of arrangement is this much. The number of new neutrons multiplied by the increase in energy per new neutron. So for example, typically in this example we have got two uh, we have uh, we have got four neutrons from four protons. So this is why the number of new neutrons in this case is 4. So whenever we have this skewed type of asymmetric type of arrangement, it will always acquire greater number of energy levels. So it will always have high energy, in the nucleus will always be of higher energy compared to the nucleus which has equal number of neutrons and protons. So this is why this will also give rise to reduction in binding energy, and the work done in acquiring this type of arrangement from this type of arrangement is called the asymmetry energy. It is represented like this. The asymmetry energy is written like this, and in this formula, the epsilon is the separation between two adjacent energy levels. This separation of is also dependent on the mass number. Greater is the mass number, smaller will be the separation. So the mass number appears here in the denominator by replacing this. So finally we get this formula in terms of A and Z, and A4 is again a constant of proportionality. So this energy is called asymmetry energy. It is also negative because asymmetry energy, which arises because of the asymmetry in the number of neutrons and protons, is negative in nature and has the tendency of reducing the binding energy and destabilizing the nucleus. So the last correction that is required is of the pairing energy. Pairing. That pairing is possible only if the number of neutrons and number of protons is even. That pairing is important to have equal number of neutrons and protons, but we saw that 60% of the of 60% of all the nuclei that exist are having even number of neutrons and even number of protons. Why? Because their existence is more probable. Why? Because they have equal number as well as even number of electrons and protons. Hence the pairs can be formed. Hence all the energy levels can be filled, and only lower energy levels are sufficient and are acquired by them. So it is not necessary that higher energy levels are filled, because no electron, no proton or no neutron is left out. So that happens in case of even case, when the number of neutrons and number of protons is even. So no nucleon is left unpaired. This is why only the lower energy levels are sufficient for them to accommodate themselves. However, if any of them, if it has odd number of protons or odd number of neutrons, or both are of odd number, so pairing is not efficiently possible, and some nucleons are left unpaired, so they tend to occupy higher energy levels. So the pairing is also playing a crucial role in deciding the binding energy, hence the stability of the nucleus. So we are considering pairing also. You see that odd nuclei are the least stable, and odd even and even odd nuclei are moderately stable, while even nuclei are most stable nuclei. The pairing energy is given by this in terms of mass number. Now it has three types of uh, options. You see, it can be negative, it can be positive, and it can be zero. Negative is when it is an odd type of nucleus which has odd number of protons and odd number of neutrons. Obviously, if both of them are odd, one unpaired neutron and one unpaired proton will obviously be left behind. If it has even number of protons and neutrons, so the pairing energy will be positive. If however, if one of them is odd and the other one is even, in that case the pairing energy shall be zero. Why it shall be zero? Because see, odd arrangement tends to reduce the energy, reduce the binding energy. Even arrangement tends to increase the binding energy, and even odd arrangement is a cancel is a sees the even arrangement has this thing that they tend to cancel each other. These two effects tend to cancel each other. This is why there is no change in the binding energy. Because the pairing energy in this case is zero. The even uh, number of nucleons tend to increase the binding energy, while odd number of nucleons, their arrangement tends to reduce the binding energy. So effect is, the two effects cancel each other, and there is no change on the binding energy in case of the middle one, for in the middle case. So considering all these three cases, we get that pairing energy is given by this formula. Now the binding energy shall be written by including all five types of energies like this. This is the formula which is given by CF Wiesacker in 1935, and in this way, by considering all these effects, all the five types of effects, the volume effect, the surface effect, the Coulomb effect, the effects of asymmetry, and the effects of pairing, by considering all five effects, we see that the binding energy can be written like this. So by substituting these values, we get this as the final formula, and these values of A1, A2, A3, A4 and A5 provides the best fit to the binding energy curve that we saw in the previous slides. So in this way, the liquid drop model is efficiently explaining the variation of binding energy per molecule with respect to mass number. So this is why it is very successful model. There is one more interesting model which also needs to be understood, that is the shell model. The shell model is similar to that of electrons. We know that in case of electrons, the arrangement of electrons in atom if we consider the shell model of electrons, we see that there are certain numbers which gives you the idea that this particular atom is going to be stable. These numbers are, suppose there are two suppose there are two electrons, or there are 10 electrons, or 18, 36, 24, these many electrons. If these many electrons are present in an atom, the atoms are stable. These numbers are associated with the inert gases. If you remember, these numbers are associated with the inert gases, and these many electrons, the atoms which are having these electrons, are relatively stable compared to all other types of atoms. So this type of significant numbers are also seen in case of nucleons, arrangement of nucleons in the nucleus, just like electrons, eh, similar to the electrons in case of atoms. So for nuclei 2, 8, 20, 28, 50, 82 and 126, these are the significant numbers. If a nucleus has these number of nucleons present in them, the nucleus is always seen has always been seen to be stable and are more abundant. These numbers are called magic numbers, because these numbers give you the idea that whether this nucleus is going to be stable or not. All other nuclei having the similar masses, they are not as stable as the nuclei having these number of nucleons. So this is why these numbers are called magic numbers. Now, why these numbers are the indication or the signature of stability of the nucleus? This fact lies in the reason for this lies in the fact that there is something called quadruple moments associated with nucleus. Quadruple, as you know about dipole, when there are two types of poles, when there are two poles, it is called dipole, and when there are four poles, two uh, when there are four poles, two of zones of positive charge and two zones of negative charge, it is called a quadruple type of arrangement. So quadruple moments are of the nucleus, the electric quadruple moments of the nucleus are responsible for their stability according to this model. And it has been seen that spherical nucleus has zero quadruple moment, and spherical nucleus is the most stable. Having zero quadruple moment is the surety of stability, and having negative or positive quadruple moment is means the deviation from the stability. So it has been seen that the nucleus which have the magic number of nucleons are spherical in shape. Hence, they have zero quadruple moment. This is why they are the most stable. This is the reason why these numbers, the magic numbers, are indication of stable nuclei, because the nuclei which have these number of nucleons have spherical shape. This is why they have zero quadruple moment. Hence, they are stable. All other type of nuclei having any other type of shape, there are two more types of shape possible: the oblate shape, which looks like pumpkin, and prolate shape, which looks like football, the American football. It is not soccer, it is rugby ball. So if the prolate shape looks like rugby ball and oblate shape looks like a pumpkin or red blood cells, so any other type shape of the nucleus will not be as stable as the spherical, because oblate shape will have negative quadruple moment while prolate shape will have positive quadruple moment. Both the cases are the cases of lesser stability, while spherical shape is the case of maximum stability. And all the nuclei which have number of nucleons equal to the magic numbers, any of these magic numbers will always have spherical shape, and hence they are obviously stable. So this is the shell model. It is just like the shell model for electrons, and we saw that the energy, the way electrons arrange themselves according to Pauli's exclusion principle, is also followed by nucleons in the nucleus. Nucleons are also spin half particles and arrange themselves in according to Pauli's exclusion principle on various energy levels. So these are the two models which have been developed to explain why certain nuclei are more stable while others are not. So this is all in this lecture. For any slip of tongue or typographical errors, uh, excuse me for that. I will be uploading the next lecture very soon. Thank you very much.